This video is about the concept of mechanical equilibrium. This corresponds to Chapter 2 in Hewett's Conceptual Physics textbook. We will cover sections 1 through 3 of that textbook in this video. Now, hopefully you have somewhere in front of you the study guide, and what you do is, as you're watching this video, when things come up on the slide and they're shaded in blue, that means there's something you need to write down on the study guide. But the study guide is just to help you to stay actively involved as you watch the video. It's not intended to limit you in any way. So if you feel like writing other notes, drawing pictures, or whatever, then please do that either on the study guide or on another sheet of paper. Things that are not experiencing a change in motion with respect to some frame of reference are in mechanical equilibrium. Look at this picture of rocks. If you saw rocks like this in real life, if they were balanced on top of one another and they were not moving, then we would say they are in mechanical equilibrium. Now, just because something is apparently motionless doesn't mean nothing is happening. In fact, what the term mechanical equilibrium means is that whatever is happening in one direction is being balanced by something happening equally in the opposite direction. What we're going to take a look at now is the idea of forces. Simply defined, we will call a force is a push or a pull. A force of some kind is always required to change the state of motion of an object. It's very important that you note the careful language that I'm using here. A force is required to change the state of motion. If an object is already in motion, that doesn't necessarily require a force, but it might. It depends on what other forces are at work. The combination of all forces acting on an object is called the net force. For example, in the drawing below, you see an airplane with 4 forces represented by arrows and words. If the airplane is flying levelly, then it is being pulled toward the ground by the force of gravity, but its wings and the way that the air is lifting it up causes an upward lift force. As long as those 2 forces are balanced, then the airplane will fly levelly. The airplane moves forward by thrust from the engines, but it encounters air resistance or drag as it flies. If the thrust is greater than the drag, then the airplane will accelerate. If the thrust and the drag are equal, then the plane flies at a constant speed. So the key idea here is that a non-zero or unbalanced force is what causes an object to change its motion. It's not a force per se. Forces might be balanced, then the object is in mechanical or some other type of equilibrium. If the forces are unbalanced, then the object changes its motion. It speeds up, slows down, turns left or right. A lot of times in this class, we're going to be studying these ideas, concepts, and then we're going to try to measure them. So the unit of force, the measurement for force in the metric system is called the Newton. When you use the word Newton as a unit of force, you do not capitalize it like Isaac Newton's name would be capitalized. However, you do use a capital N to abbreviate it. You'll run into this a lot when there's a unit named after somebody. It's a lowercase word, but an uppercase abbreviation. A new term that we also need to introduce at this point is the term vector quantity. Force is an example of a vector quantity. Now what that means is it's a measurement that needs both a magnitude or size and a direction in order to completely describe what's happening. Force is a vector quantity. Velocity is a vector quantity. Another term that we've used in an earlier video was displacement. That's also a vector quantity. It needs both a size and a direction. When we represent vector quantities on paper, we draw them with arrows. Those arrows are called vectors. So a vector is an arrow in a diagram that represents a vector quantity. For example, in the previous slide, the arrows represented vectors of the various forces at work on the airplane. One thing that's important to keep in mind is that vectors should be drawn to scale, at least some sort of comparative scale, and the direction that the arrow points is important. I'll show you that in just a minute. Before we do, I want to contrast vector quantities with other types of measurements called scalar quantities. Scalars have no direction. They're not depicted by arrows. They're measurements that can be described by size or magnitude only. Things like area and volume are scalar quantities, and so is time. Time always goes only in one direction, and so it doesn't really have directionality in the strict sense. You always know which way is forward. There is no backwards, up or down. So time is a scalar. Here we see a vector that represents 60 kilometers per hour to the right. The scale is shown as 1 centimeter equals 20 kilometers per hour. So the arrow is 3 centimeters long. Here's another where it's only 2 centimeters long, so this would represent a velocity of 40 kilometers per hour. But you'll notice that this one points up, whereas the last one pointed to the right. The direction matters for a vector. You do not use arrows for scalar quantities. If you have a scalar, it can be added, subtracted, multiplied, and divided just like an ordinary number. For example, if 2 liters of water are added to 3 liters of water, the result is 5 liters of water. In contrast, if something is pulled by 2 forces, which are vector quantities, if one has 2 newtons of force and the other has 3 newtons of force, the result may not be 5 newtons if they're not going in the same direction. With vector quantities, direction matters. Just for a little practice to make sure that we're on the same page, take a look at this diagram. There's an object here with 2 forces pushing it toward the right. One force is 5 newtons, the other is 10. The net force are those 2 forces added together, and since they're in the same direction, the net force would be 15 newtons to the right. A force is a vector and should have both a size, 15 newtons, but also a direction, to the right. That direction may be represented by an arrow. Here's the same object, 2 forces of 5 newtons and 10 newtons. This time the forces are in opposite directions. The net force would be 5 newtons to the right. You designate one of the vectors as positive, the other as negative, and then add them together. But of course, when you add a negative, what you really do is subtract. And finally, here's the object with 2 5 Newton forces acting in opposite direction. the net force is 0. This object would be in mechanical equilibrium. It would be motionless, stationary. Here's a picture of a girl holding up a rock. Now, if you imagine yourself doing this, you know that your muscles will be doing work to hold the rock up. You can feel your muscles pushing upward. The Earth's gravity is pulling downward. You are pushing upward. As long as those two forces are equal but in opposite direction, the rock will not move. But upward directed forces don't require muscles necessarily. For example, you could just hang something on a string or a spring. Here's a picture of several springs with different objects hanging on them. We say that the springs have a tension force, or we will just call it tension. So tension is a stretching force. Now, why are the springs stretching? Because the objects suspended on them have different weights. But what you need to recognize is that there are actually two forces at work. Weight is the gravitational attraction between an object and the earth. Tension is the force that's pulling upward. As long as those two forces are equal, these objects will be stationary. In the United States, we measure weights in units called pounds. In the metric system, most of the rest of the world uses newtons, are units of weight. But I thought newtons measured force. That's right. Tension is a force and would be measured in newtons. Weight is also a force. It's the force of attraction between a mass and the earth. Since it is a force, it is appropriate to measure weight in newtons. So if you're standing on a scale, it measures your weight. It's actually measuring the force of attraction between your body and the earth. There are lots of different kinds of scales. The one shown in this picture here is called a spring scale. Basically, if you put something on the hook, the slide will come down, the numbers will go up. So for example, here are two forces at work. The sugar, the weight of the sugar pulling downward, and the tension on the spring scale, which is hooked to the ceiling, pulling upward. The scale reads 2 pounds or 9 newtons. The tension force and the weight are equal, but they are in opposite directions. Therefore, the net force on this bag is 0, so it remains at rest. Mechanical equilibrium is a state wherein no physical changes occur. We say that whenever the net force on an object is 0, the object is in mechanical equilibrium. This is known as the equilibrium rule. Whenever the net force on an object is 0, the object is in mechanical equilibrium. The equilibrium rule can be expressed mathematically. If you look in the blue square here, you see a funny looking letter, something like an S or an E. That's actually the Greek letter for our capital S. We people in America call that sigma. So sigma in mathematics usually represents the sum of whatever it's touching. So in this case, the sum of F, where F stands for forces. So that sigma F is just shorthand for add up all the forces, and then if it's in mechanical equilibrium, they should equal 0. So for example, in the previous slide, the suspended object, the force had an upward tension and a downward weight. They were equal in magnitude, opposite in direction, so the force up and the force down add up to 0. That's mechanical equilibrium. Here are two people standing on a scaffold. These are window washers. Each of the window washers has a weight, and the scaffold has a weight. Those weights are directed toward the center of the earth. The earth and the objects are attracting each other with a certain amount of weight. The ropes have tension forces acting in the opposite direction. If the scaffold is not moving, then the sum of those forces must be 0. Therefore, mathematically, you could say the three weights represented by W1, W2, and W3 must add to the two tension in the ropes, T1 and T2. They must add up to 0. As long as the scaffold is in mechanical equilibrium, it won't be moving up or down. Here's another situation where a gymnast is hanging by two rings. If we could put a scale on these ropes, what do you think they would say? Now she changes one of the ropes and rings just a little bit, moves it over so that she's hanging a little bit more weight on her right hand than on her left. What do you think the scales would say now? Well, in the first case, when she hangs equally, she has only one weight. So if there's two tensional forces, they have to split that weight between them in order for her to be in equilibrium. Otherwise, she's going to be moving. If she's hanging steady, then the weight down and the tension up must be equal. But the tension is divided into two ropes. If it's divided equally, then those two equal tensions and the weight down will add up to 0. But in the second case, she's putting more weight on her right hand than her left. And so if we had some sort of spring scale hooked up here, we should see that the one on the right is actually greater than half of her weight. The one on the left is a little bit less than half of her weight. But again, since she's not moving, whatever her weight is downward, the tension upward must be equal. And so if we added these two quantities together, a little bit greater than half her weight, a little bit less than half her weight, it should add up to the same number that it did before. Now, instead of hanging from a ceiling, a lot of times what we see are things sitting on top of other things. In that case, we are going to talk about something called a support force, also known as a normal force. So a book lying on a table, for example, has a weight because it is attracted toward the earth, but the table supports the book, and so there's an upward force in the opposite direction of weight. We don't call this tension since it's not hanging. We're going to call this the support force or a normal force. Those are synonyms. So the upward force that balances the weight of an object on a surface is called a support force or the normal. The upward force that balances the weight of an object on a surface is called the support force or the normal. You can also call it the normal force, but like tension, we usually just say tension, weight, normal. We don't add that extra word of force. Now it's kind of hard for us to imagine that an inanimate object like a table can somehow exert a force. But the table really is pushing up on the book. By the way, if we put numbers to these vectors and then added them together, we'd have to designate one of them as positive and one as negative. Traditionally, vectors pointed up are positive. Vectors pointed down are negative. Similarly, if we have a vector to the right, we will call that positive. If we have a vector to the left, we would call that negative. So in this case, the normal or support force is positive, the weight is negative. If the book is not moving, then the net force on the book must be 0. The normal and the weight must have the same size, just opposite directions. Mathematically, we could say the sum of the forces, normal plus weight, equals 0. As I mentioned earlier, it's hard to imagine that the table can actually be exerting a force since it doesn't have a brain and it doesn't have muscles. That force actually comes from the atomic level. If you could look at a solid object like a table on a very submicroscopic level and see the actual atoms, you would observe that the atoms are not actually touching each other. They might be very close, but not quite touching. They don't touch each other because they have electrons on the outside. All atoms have electrons circling them. Those electrons are all negatively charged. And when you have two charges of the same type, both negative or both positive, those charges will repel each other. They'll push each other apart. So atoms stay slightly apart from each other because of the electrons that are encircling them. When we put the book on top of the table, we're pushing some of those atoms a little closer together than they were before when they were in equilibrium. They're going to push back to try to separate. Those electrons do not want to get close to each other. They will push backwards. And so that weight actually comes from this atomic level sum of forces in the upward direction in this case, because the weight is directing the atoms downward, trying to squeeze them together. So here's a bathroom scale, person standing on it. What is the net force on the bathroom scale if this person weighs 110 pounds? When you read physics problems, you have to read them very carefully. The question asked, what is the net force on the scale? Well, the scale is not moving. So the net force on the scale is 0. The upward normal or support force is equal to, but an opposite direction from, the downward weight. Since the scale is at rest, the sum of the forces equals 0. Incidentally, a bathroom scale like this is reading the normal support force, not the net force. Earlier, we had an example where a gymnast was hanging by 2 rings. What if we were standing on 2 scales? If you distribute your weight equally between the 2 scales, what do you think they would read? What if you now leaned over a little bit in one direction or the other? You'd be putting more of your weight on one foot than the other. Do you think the scale would show that? It sure would. When you have your weight equally distributed between 2 scales, the readings on each scale is half your weight. But if you put a lot of weight on one leg or the other, then that side will have a much greater weight than the other. But in both cases, they should add up to your weight. That brings to an end the first part of Chapter 2. And so what I'd like for you to do at this point is make sure that you've either read or that you go back and review Chapter 2 in Hewett's Conceptual Physics book, sections 1 through 3.